Now we'll go on to the second part of our lecture, which is about how a FinFET is fabricated. But first we'll start by remembering how a planar CMOS is constructed. So this is a real high-level overview, but in general, we start with a substrate, usually p-type. Then we grow on top of it a thin oxide, which will be the gate oxide, and on top of that we grow a polysilicon layer, which is going to be the gate material. Then we can pattern our gates and etch away what we don't want. Okay. Then we're going to grow on top of it another level of oxide, and we're going to form our sources and drains, and we're going to use all kinds of self-aligned processes to make this happen. Then we're going to go into the back-end layers, which are going to be litho, etch, clean, deposit, and polish, and do that over and over again. So we're going to grow our ILD, our interlayer dielectric, then pattern our vias or our contacts. We're going to drill down our contacts, etch them away. We're going to then fill that up with a dual damascene type of a process. We're going to have our contacts and our metals formed. We're going to then etch away the excess metals, and that's kind of the type of process we're going to have. So that's how we basically made a planar process. Of course, it's much different than that, and there are different types of flavors and different types of ways and a lot of different techniques that have been developed over the years. But just in a general type of a way, that's how it's done. On the other hand, when we go up to the FinFET, we need to make these fins that are above the substrate plane. So how are we going to do that? Well, we're going to carve them out of the substrate. So we're going to grow on some sort of a hard type of a layer. We're going to pattern our gates, and then we're going to etch away everything underneath, leaving only these fins behind. And that's how we have our fins over there. Then we can go and we can fill this stuff up with oxide, etch it away, okay? And we can cover everything with oxide and with poly, and actually this brought us our FinFET as we can see it over here. So we're going to etch out these fins, these guys over here, and we're going to then and then we're going to cover it with our gate, which is going to go on the 3 dimensions over the top. So our thin oxide is over here, and our gate goes over it on this type of an area. So in general, during scaling over the last probably 20 years or so, what we've been trying to do is move to higher performance. And how do we do that? Well, 3 main vectors are increasing the mobility of the channel, and that's been done really through strain engineering, which we'll be discussing a lot. Another thing is to increase the COX, the capacitance that goes from the gate to the channel. That will help us move more carriers. It'll bring in more carriers into our channel, and it will help us move more carriers. And for that, we want a high K dielectric and use a metal gate. And the third vector, of course, is to decrease L, which is what has been going on for the length of Moore's law, make our transistors critical length smaller and smaller. That's steepening the hill, and that we're able to do through lithography scaling. So this has really been done over the years, and we can see here, this type of a plot from Intel, which shows their 90 nanometer process in 2003 till their 22 nanometer FinFET process in 2011, and how they started off with strained silicon all the way back, around 65 nanometers. They went to high K metal gate around 45 or 32, and finally went to the 3rd dimension to these FinFETs in 2011. Okay, and everybody came after Intel at this type of a point. And really, so we use mechanical stressors in all of the foundries around 40 nanometers. We used high K metal gate and replacement gate around 20, 28 nanometers. Multiple patterning used around 20 nanometers, and complex middle end of the line around 20 nanometers. And we'll be discussing all those things now. So we have a bunch of things that we need to go over, and we'll start with how we pattern the fins and the gates. And the fins and the gates are really the first critical step of the process, where we need to make these really, really, really thin fins. These guys over here, which are our source and our drain, and really they're the smallest part. They're very, very thin. They have a very tight pitch, and we need to build tightly pitched gates around them. And you can see here just this kind of a plot showing you how scaling has worked. We kind of use this this type of design and technology co-optimization type of a thing. And you can see here that the fin pitch of Intel 14 nanometer was much higher than the fin pitch of the 10 nanometer, nanometer, even though probably the fins actually stayed at the same size. It's just the pitch and the got much tighter, and that enabled us to make our standard cells smaller and therefore get our higher density of transistors in the design and keep up Moore's law. But how do we actually do this with 193 nanometer lithography? So the 14 nanometer and the 10 nanometer process at Intel were done with this 193 nanometer lithography. And remember that the critical dimension of our design, it's a factor of some sort of a constant time the wavelength, and the wavelength has been 193 nanometers divided by the numerical aperture, which is this of the laser, which is the substance we've been going through times the factor of the lens. Okay, so how do we do this? Well, with a lot of tricks. Immersion litho is the first one. Phase shifting is another one. Double patterning, self-aligned patterning. And we're going to be discussing these second two. So immersion litho is actually taking this N, and instead of using just air, which the N is 1, we'll use all kinds of liquids, which have a higher refractive index than air. Phase shifting is doing all kinds of games with the masks and so forth. Of course, bigger lenses can give us bigger sine alpha, but that's really hard to do. Okay, so what has really made us been able to make these very small pitches is double patterning and self-aligned patterning. In fact, without these two tricks, we're able to make about 80 nanometer critical dimensions, something like that. So the first one is double patterning, or what's also known as litho etch, litho etch. It was first introduced in 45 nanometers by Intel and later by the other foundries. And we usually, as back-end people or layout people, we call it colored masks. So what that means is that we're taking two different masks and we're doing pitch splitting using these two different masks. So let me show you what I mean. We have our substrate over here, and we grow some layer over it and put our photoresist on top of that. And then we bring in our mask, which has its minimum pitch. And remember, this minimum pitch is somewhere around 80 nanometers or something like that, 76 nanometers or so. So again, we have a mask that doesn't do anything fancy. It just uses a minimum pitch between it. And that is our red mask. So we go and we pattern our photoresist with that. You see that these purple areas have been hardened or have been developed or whatever. Okay, then we go and we bring in our second mask, and it's a blue mask. And again, this mask is also using a minimum pitch for its slits over here, and that's fine. But the difference is that it's shifted from the first mask, and then when we expose it, we can get another pattern, and you see that we have now something that is lower than our minimum pitch. So now we have something that is like half of our minimum pitch just by using two masks. This is limited by misalignment between the masks. So when we get to really, really small dimensions, we have to make sure that the mismatch between where we put one mask and the other is small enough that we won't ever get problems over here. And so we can't keep on doing this forever. We can do it with two masks, maybe three, having litho etch, litho etch, litho etch, but then it gets pretty hard and causes variation and causes yield problems. What saved us with that is what we call self-aligned double patterning. Okay, so we can also do this, get this double resolution with a self-aligned technique. And self-aligning things is what really saves us, where we don't have to make a perfect alignment between mask steps, because then the misalignment between mask steps will really limit us. So how does this work? So we take a substrate, we put some sort of a hard mask on top, we put an oxide on top of that or something like that, and we put another type of a hard mask or some sort of other material on top. And then we define our what we call mandrels with a minimum pitch of our design. Okay, so we built these mandrels and they're very nice, and this is built with the minimum pitch of the design. We didn't do anything fancy here. Again, we used our minimum pitch to define some sort of a structure over here that's sitting on top of some other stuff. And we call these, again, mandrels. Okay, what we then do is we fill up another material on top of it. And if you can remember how spacers are made, this is exactly how spacers were made. And the important thing to pay attention to is by filling a certain amount on top of these guys, we get this bumpiness. And the bumpiness means that the height over here and the height over here is the same, but the height over here is much larger. And then when we etch away, and if we etch away a constant amount, what happens is we're left with these guys over here, which are called spacers, okay? And again, we use this for making things like lightly doped drains in planar technologies, but now we actually used it to make a spacer around the mandrels. And now we can just remove the mandrel itself, and we get some sort of a pattern that has half pitch from the minimum pitch, and it's completely self-aligned. It's really nice. So we remove the hard mask, and the spacers are at half of the minimum pitch, and that's really good. And that way we got a higher pitch than we could have with a standard lithography. And you have to also note that the line edge roughness is correlated for both sides of the mandrel, so it really reduces the L variation, and really we got a win-win situation. And self-aligned double patterning has been the thing that has been used. But do we stop there? And the answer is no. We can go even farther and use self-aligned quadruple patterning. So now we have these these spacers which are at half pitch, and we use them as the mandrel for another type of a self-aligned patterning. Okay, so we just repeat the process. Okay. We remove those guys, and we build another spacer around what was underneath, and voila, what do we get? We get a quarter pitch. So that's self-aligned quadruple patterning. I guess that should be SAQP. Really, if you see here, these are pictures of this type of self-aligned quadruple patterning, and that's what is used today to make these really, really tight pitches in up to 7 nanometer design, and mainly, again, for the fin layers and maybe the gate layers is where it's done. So, advanced litho points besides that. So, one thing is that with this operation that I showed before, you can really only print one line width. So we need to do other tricks in order to make multiple line widths or to make different spacings between them. We can use block masks and make different mandrel widths, because remember, the mandrels were actually made with just a regular type of photolithography. So there we can play around with the width. But again, this will take, to make these block masks and to play all these tricks, we need additional steps. And all of these things take a lot of steps. They take several masks, and steps and masks are cost. Their costs, their time to fabrication, and it's not easy to do. So each multi-pattern layer is unidirectional. Everything we did here didn't discuss all kinds of turns and so forth and so on. So when we use this type of double patterning for back-end layers or middle end of the line layers or these types of layers, we cannot do any wrong way routes or jogs. Obviously for the fins and for the gates, we have no breaks at all. But even with the lower metal layers, which we'll call things like metal 0 and so forth, as we'll see later, we cannot do any wrong way routes or jogs. We really have to use a via even if we want to make a small jog. Okay, another point is, and this has been used for quite a long time, and with the metal layers as well, we use what we call orthogonal cut masks to break patterns. So we made, say, our fins or our polys with these like beautiful like straight lines, and we saw how we could make these beautiful straight lines with this self-aligned patterning type of stuff. But when we just use regular type of masks, what we get is, because of refraction and so forth, we don't get pretty things. We get these like these curvatures at the ends. However, if we just use that in an orthogonal fashion, so we already built, like in this case, it's the poly inside an SRAM, and we built it really pretty and straight out over the whole thing, what we can do then is make a cut mask that's just where we're going to etch away, and we don't care that there's this curvature here because the curvature falls in between two of these lines that are already printed. But where it cuts really beautifully and straight, and we get a very pretty rectangle over here. So that is something that's done, and this uses standard lithography at the minimum lithographic pitch, which I said is around 80 nanometers. So that's something that's done. We do it on the polys, we do it on the fins, we do it on the low metal layers, we do it on the low diffusion layers, and so forth. So that eliminates corner rounding on fins and gates, and so we have these cut masks that we'll be seeing when we discuss layout later on. Another point is that we use self-aligned vias. So in any case, we want to do this self-alignment not to have all kinds of problems, and we'll be discussing how we do it on the middle end of the line stuff, but also on the vias. So we put on these hard masks on top of where we want to put the via, and then we actually put the via mask on top of that. So just in case we have this misalignment with the via mask itself, we're not going to make any problems because it won't etch through these hard trenches and it will stop there. So that's we might not get a perfect via in terms of its size, so maybe its resistance will be higher, but at least it will not puncture through and possibly short to a different metal layer. So we're going to see that with our self-aligned contacts, and maybe you'll understand it probably there better. So we finished talking about, the fins and the tightest pitch we have to get in the smallest features. Now let's go over to the source drain regions. Okay, we have a few problems with the source drain regions. They're really small and they're delicate. Remember, these fins are tiny and they're actually freestanding up on top of the silicon substrate. So they're really hard to contact to. The second thing is they have real high resistance because remember, it's not a very low resistant material. It's some sort of a silicon, right? So it's some sort of semiconductor, and so with such a thin semiconductor, it has high resistance, which adds to our source drain resistance, which is not something that we want. And the third thing is that we want to apply stressors to improve mobility. We've been applying stress, as we'll discuss in the next slide, for several generations now to really improve the mobility, and we want to do that with the FinFETs as well. So how are we going to do that? We actually use epitaxy to do this. So we start by building a spacer around the gate. So this green area here is a spacer that we build there so we don't accidentally short between the gate and the source drain. Okay, and then what we're going to do is we're going to grow an epitaxy layer. So growing an epitaxy layer is growing a semiconductor layer on top of some sort of substrate on top of the layer that's already there. So the fin is the silicon that was the substrate itself, and we grow on top of it an additional layer. And this epitaxy layer, it can be a different material. It doesn't have to be silicon. So we use a layer that's going to apply stress to the channel, and that's how we build our stressors. So this both gives us a much larger area and a stronger type of a structure for landing our contacts, but it also is able to apply stress, and we can also do it with different silicon orientation here for the best stress and mobility that we want. The result is this diamond shape. Now, it's really interesting. So the diamond shape comes out much more profound in a PMOS device than an NMOS device, and you can see that over here. And in fact, applying the stress also has worked much better on PMOS devices than on NMOS devices. So just again, a bit about stress. What is stress? So silicon channels they're piezo-resistive. They're kind of like a spring. The straining the lattice affects the mobility. So that happens when we do tensile stress. In other words, when we're pulling away the size of the channel, we're improving the mobility on the NMOS, and compressive stress, when we're pushing in the lattice, it's improving the stress on the PMOS, and that has been done for several generations now in planar devices. It also really depends on the lattice orientation. And interesting here, if CMOS was, if regular planar devices were always at a 1-0-0 orientation, now we have we have the sides, which are at a 1-1-0 orientation, and the top, which is at a 1-0-0 orientation, and the strain affects it differently. Okay, and again, as I mentioned before, strain has really been more effective for PMOSs, and you can see this graph here that shows the N/P ratio, or what we call the beta ratio, which used to be, when we teach it in our textbooks, we say that the NMOSs have mobility that's like 3 times as high as the PMOSs. Well, that's been going down for many generations, and the main reason is because of this stress. And really, at 7 nanometers, it's fallen to about unity. So PMOSs are really, we can have our PMOS and our NMOSs to be equivalent to each other, rather than have double the size PMOSs than NMOSs, as we learned in our previous courses. However, with nanosheets, that is expected to change, because we have, again, different orientations and so forth, and the stress becomes less effective or less dominant for PMOSs than it is for NMOSs. So the next point we want to talk about is our high K metal gate. So there are 2 problems with the transistor gate. The first one is that when we thin the oxide, we got gate leakage. And the second one is by using polysilicon, we first of all had high resistance because it's not a conductor, it's a semiconductor that's highly doped. And we also had polydiffusion, which made our effective gate oxide thickness be larger. Okay, so those are two problems that we had with the traditional transistor gate, and therefore already at 45 to 28 nanometers, we changed and we started using high K high K oxide with a metal gate. So what is a high K oxide? You can see here that silicon dioxide has a dielectric constant, which we can call a K or a kappa, of 3.9, and things like hafnium dioxide, they have a K of about 25. So that's, an order of magnitude higher almost. And if we can do that, if we can have such a higher K, we can keep the same transconductance while using a thicker gate, and we can reduce the gate leakage in that way. So we can actually do that and continue oxide scaling to a point without getting a gate leakage that's too high. So that was one thing that we had. The other thing is that metal gates improve resistance. So we can replace our polysilicon with a metal gate. We don't have the resistance of the polysilicon. We have better resistance of, some sort of copper or something like that. And we also don't have this problem with polydiffusion that, again, hurts our effective oxide thickness. Okay, so that's why we moved to high K metal gate once we were able to integrate these high K materials into the process. However, the high K materials have a lower energy band gap, and metal gates are sensitive to high temperatures during annealing, so we have to do all kinds of tricks. Before I discuss that, I just want to tell you about the metal gate and the VT adjustment. So we said originally that the VT of a transistor is set by the work function difference between the gate and the substrate. Where when we say work function, we mean the energy gap between the vacuum and the Fermi level of a material. So when we look at the metal side or the gate side, it's one thing, and we look at the substrate side, it's another thing down to there. And the difference between the two, that's the work function, the work function difference. And this FMS, or this work function difference, it's one of the main things that causes our VT. Then we have the doping and the junction and the backgate capacitance, which also affect this, as we learned in our previous courses. However, what happens now in older technologies, that gave us some sort of a VT, and if we wanted a high VT device, we would add some doping in the junction. We would add this guy or remove some doping in the junction. We get high VT or low VT devices and so forth. But remember, I said random doping fluctuations, RDF, it was really a big problem because we got to a point where we had 100 or even fewer dopants to use to set our VT, and this was it caused huge variation, and that therefore we went over to intrinsic channels that don't have doping inside the junction. And now we need to set, if we want to have high VT and low VT devices, or we want to set our VT to be different than whatever comes out just because of the work function difference between, our copper metal and our silicon substrate, we have to do all kinds of other things. And so how we do it is we use special metals that have a work function difference that is of our choice. So that is called a work function metal. Okay, so what we do basically now is that we have a high K material over here, then we have some sort of a work function metal, and then we have our low resistance metal, because the work function metals tend to be higher resistance. So we close to the gate oxide, we put this work function metal, which we can choose different metals, and therefore we can get our high VT, low VT, ultra low VT, etc. And then we fill in the rest of it with our copper interconnect, which has low resistance. However, this is problematic, so we have to use what we call a replacement metal gate process, or an RMG. So metal gates are sensitive to high pressure process steps that are required for source and drain engineering. So we have to do, this epi type of stuff, which needs really high temperatures, and that basically melts away our metal gates and ruins everything we just discussed about setting our VT. Okay, so there we moved over to what's called a gate last approach already in planar devices several process generations ago. So how is this done? So first we form the gates. We use a polysilicon layer. We call that a dummy layer, dummy gate. Excuse me. So as you can see here, these guys are dummy gates. They're pieces of polysilicon that are filled in. So we don't put a metal gate at the first stage. Okay. Then we go and we make our source and our drain. Okay, which is these guys, the source and the drain. We had to use these epi steps to put in our stressors and to build our our extra sized raised source and drain, and that would have ruined the metal gate, but it didn't ruin the dummy gate, which is made out of polysilicon. Then what we're going to do is we're going to partially fill in the area there. We're going to remove our dummy gate, as you can see here. We're going to fill it in with a barrier layer, because if we want to put in something like copper, it's going to diffuse into the silicon and cause us trouble. So we have to put in a barrier layer, and then we can fill it with a work function metal, and then fill it with our copper. Okay, so that's called replacement metal gate, or gate last. Okay. However, this type of process, it also impairs the silicide. So if you remember, we do silicidation over the source drain, and we used to do it over the poly as well to reduce the resistance of the source drain. But these types of steps, they also impair the silicide. So again, we do this silicide last type of a process. So these things, what I want to kind of point out here is there are many steps that are required to do this, with many different masks and so forth. And that makes the process, this whole front end process, it can be really hundreds of masks just to make the transistors themselves. With that, we go over to what is called the middle end of the line. So if we were talking about older technologies, we never discussed contacts as anything special. In fact, what we needed here is we had, our gate, and then we had some sort of distance, which brought us our contact, and that was okay. The contacted gate pitch, which is the distance between the contact and the gate, basically, it was large enough to place the gates and the contacts next to each other. But as we tighten the pitches, when we get this contacted gate pitch becomes closer and closer and smaller, misalignment, again, can cause us to accidentally have the contact, fall on top of the gate and cause a short here, and that's something that we don't want to happen, obviously. So therefore, self-aligned contacts, or SACs, were introduced already in nanoscaled planar technologies. So how is that done? What is a self-aligned contact in a planar technology? You basically take your planar device, and after you build the gate with the spacers around it, you recess the gate. So you etch away a little bit of the gate, as you can see here, and you fill it with an etch stop, a hard mask that will stop etch when you use an etch step that's sensitive to this type of a material. And then you throw down your contacts, and when they hit this etch stop, they won't go through it. So you'll never have a short between the contact and the gate, even though you may have had misalignment where the contact accidentally fell onto the gate. But it doesn't actually contact the gate, it just hits the gate. But now we do have this type of a layer on top of it, which we have to break through in order to contact the gate. And that's not a problem, because if you remember, the gate goes out here, and we stick the contact on somewhere outside the transistor, the channel area itself. So that's a self-aligned contact in nanoscaled planar technologies. And because it's more complicated, we started calling this a new name, which is middle end of the line, or MEOL. It's no longer just the front end of the line, which was the transistor development, which we discussed up till now, the fins, the gates, the source, the drain, the high-K metal gate, etc. But now we have another, and then the back-end layers, which are the metals and the vias. But now we have a middle end of the line, which are actually the contacts to the source, drain, and poly gates. Okay, so with FinFETs, it becomes really complicated, and we need a lot of extra steps. So first of all, this RMG, this replacement metal gate, is harder to recess than in the previous type of way of doing it with a gate last approach. And the other thing is that Intel wanted to have what we call a coag, or a contact over gate, in their 10 nanometer process, and now TSMC also has it in 5 nanometer process, and so forth. So what that is as we said, we used to pull out our our gate layer, our poly over here, and then contact it somewhere outside the cell, but that's really wasteful. Instead of that, what Intel wanted to do at 10 nanometers, and did, is to put the gate contact right inside the on the channel itself, and therefore save a lot of area. And this they did. It cost them a lot. In fact, one of the biggest problems for Intel ramping up the 10 nanometer process and getting to higher yield is all this middle end of the line, which was really problematic, and specifically this contact over active gate. So in order to do that, the middle end of the line has many steps. So again, the first thing we're going to do is we're going to cap the gate. So we're going to cap the gate, and that's done. So when we put our contact down, it's what we call self-aligned, that if it falls accidentally on top of the gate, it won't actually short it because we have this hard stop on top of that. But then we want to do the same thing, and we want to stick our a contact on our gate, which we can see over here. But in order to do that, we want to make sure that we don't accidentally short to the source and drain. So we have to cap the source and the drain over here, as you can see, and then we can dump our gate contact, and it's also self-aligned, so it will not, if we have misalignment, accidentally short the gate over here. So now what we have is a hard mask that's sitting over our source and drain, and so in order to actually contact our source and drain, we have to go and we have to add another via layer, which we call via 0 or something like that, to break through this guy. So we have an additional via layer, and we'll see that in the layout in a few minutes. So there are disadvantages to this. We get really high gate to source drain capacitance because you see these things are very close together, and there are a lot of these layers over here and so forth. We also have, of course, the high source drain, middle end of the line, and lower back of the line resistance because we have these very small things. They also often don't come out well, so they're really tight over here and so forth. So we have high resistances, and of course that this is, this can be dozens or more masks and steps to actually print these things, which costs a lot in the end. It takes a lot of time, it costs a lot. It's really problematic, all of these steps. So that was middle end of the line, and going now into the back end of the line. So as we have discussed in previous courses and so forth, copper interconnect replaced aluminum a long time ago, and this was important because it really provided lower resistance and improved electromigration. And the way this was achieved was through what we call the dual Damascene process. So taking a certain metal layer, this over here, a copper metal layer, we put some sort of a barrier over here. So this barrier makes sure that the copper doesn't diffuse into the interlayer dielectric, and we build our interlayer dielectric, which is some sort of a Loke material on top of that. What we're going to do then is we're going to puncture through the interlayer dielectric to where we want to have our via. So this is our via. Okay, and then we're going to be able to fill that in with copper, and that will create our via. However, what we do is in the dual Damascene process is then we pattern our metal layer on top of that. So this is now our metal, if this was metal 1, then this is our metal 2, and this would be via 1 or something like that. Okay, and then we fill the we fill the whole thing in with a liner and a barrier layer that again makes sure that the copper doesn't diffuse into the interlayer dielectric, and fill that up with our interconnect material. And then we etch it away and take off the liner at the top. So that's the dual Damascene process, and that's how we were able to use copper and put it into our process. But as we saw here, we need this blue kind of thing that I drew here. That's a barrier, a liner, and a seed layer. So basically, we have this barrier layer. This one over here, it's a type of a material that separates or isolates between the copper, which is going to be our main interconnect material, and the interlayer dielectric, because copper will diffuse into the interlayer dielectric and it'll be really bad. That's actually what was really hard to get copper used for many years. Then we have a liner, which is another type of a material that helps everything stick together well and not have all kinds of opens and so forth. And we usually put some sort of a seed, which is something that the electroplating can help catch the copper. So these three layers, the problem with them is they're really small and they don't scale. And then when we go and we scale the interconnect layer, so we get better lithography, right? And we go from a pitch that's this big, we go to a smaller pitch and to a smaller pitch. The whole thing scales, but this threesome, doesn't scale. It still takes up the same room, and it leaves us with very little material here that's actually low resistive, and that's real bad because it increases the resistance of going through these metal layers. So that's really bad. The answer to that is that at the real tight pitched metal layers, which are the low local interconnect layers, copper is not good anymore. Actually, cobalt and rubidium and these types of materials, even though they have a higher resistance coefficient, a higher sheet resistance, when you take into account the barriers and so forth that are needed, which are not needed in cobalt, then you actually get better resistance with cobalt, and you get much better electromigration protection. So Intel already put cobalt into their chips at 10 nanometers, and other fabs have been doing it also since then. And that was another thing. Putting any new type of material into your process is really tough, and that was another thing that really hurt Intel's ramp up of this process. So that is all I wanted to discuss now about FinFET fabrication. And if you have any questions, please ask in the comments.